Centuries ago, master builders achieved the impossible with little more than stone and human ingenuity. Their Gothic cathedrals still scrape the sky, silent monuments to a forgotten technological revolution. We often assume such marvels required modern tools, but the truth is far more fascinating. By the end of this journey, you will understand the hidden engineering that let medieval minds construct these stone giants, knowledge that reshapes what we believe is possible. How did they lift multi-ton blocks to dizzying heights without cranes, or carve thousands of unique stones that fit together perfectly? What does their silent, stone language tell us about human ambition? Gothic ambition did not arise from an empty landscape. It was a powerful reaction against the heavy, earthbound churches of the Romanesque era. Those older structures were built for fortification and spiritual introspection, with thick walls and small windows that kept the world at bay. But a profound shift in thinking was underway. A new theology emerged, one that envisioned the church not as a fortress against a fallen world, but as a gateway to a divine one. The goal was to use stone and glass to create a vision of heaven right here on earth. This was a spiritual and architectural revolution, a desire to flood sacred spaces with literal and metaphorical light. Yet this breathtaking vision would have remained a dream without a parallel revolution happening in the bustling towns below. An economic boom was transforming Europe. Trade routes flourished, craft guilds amassed wealth, and cities competed for prestige. A magnificent cathedral became the ultimate statement of civic pride, a project that could unite a community and attract pilgrims and their wealth from across the continent. Powerful bishops and wealthy merchants saw in these soaring structures a testament to both their faith and their city's importance. They poured vast resources into what were arguably the most ambitious public works projects of the entire millennium. So we have this powerful convergence, a perfect storm of spiritual yearning and earthly prosperity. But how do you translate a bishop's divine vision into a physical reality that defies gravity itself? The first challenge was one of sheer weight, and the solution was found in a radical new shape that would become the very skeleton of Gothic engineering. These master masons were the undisputed chief executives of the medieval building site. Think of a man like William of Sense, who traveled from France to England after a fire devastated Canterbury Cathedral. He did not carry a roll of detailed architectural plans. Instead, he carried something far more valuable, a mind trained in the sacred and practical secrets of geometry. His authority was absolute, his vision guiding every carved stone and placed block for the decades the project would demand. He was the architect, the structural engineer, and the general manager, all fused into one role. The true blueprint for these stone giants existed not on parchment, but in the master's mind and in the temporary drawings made on a full-scale tracing floor, a large flat surface of plaster or stone where designs were sketched out in charcoal and chalk. This was a living plan, constantly refined and adjusted, accessible to the senior craftsmen, but ultimately directed by one person's overarching intelligence. How could such a monumental undertaking not descend into chaos? The master mason operated through a pyramid of trust. He led a team of under-masons who themselves directed the layers and the carvers. Each level possessed its own specialized skill, from the precise squaring of stones to the intricate carving of foliage for a capital. The master did not need to micromanage every cut. He established the key proportions, the critical angles, and trusted his trained guildsmen to execute their part of the grand design. This hierarchical system, built on shared knowledge and mutual respect, turned a sprawling construction site into a symphony of coordinated labor. And at the very heart of that shared knowledge was a silent, universal language, one that could be understood by a mason from any land. This invisible skeleton was geometry, the sacred language of the medieval master mason. For these builders, geometry was far more than a practical tool. It was a form of divine revelation. They held a profound belief that God had constructed the universe itself using perfect geometric principles, and by using those same principles, they could create a building that resonated with the harmony of creation. Their quest was to make stone and mortar sing with cosmic order. The tools to perform this magic were astonishingly simple: a compass for drawing perfect circles and arcs, and a straight edge for drawing unerring lines. With just these two instruments, a master could generate the entire complex plan of a cathedral, from the sweeping curve of an apse to the precise points of the vaults high above. The entire design was a cascade of shapes born from a single starting point, often a perfect square. By drawing arcs and connecting intersections, that initial square could generate the root 2 rectangle, a shape with sides in a ratio of 1 to the square root of 2, which in turn could define the proportions of the nave. The equilateral triangle, a symbol of the Trinity, was another fundamental building block. Rotate a triangle, inscribe it within a circle, and you could derive the perfect angles for a vaulted ceiling or the precise layout of a chapel radiating from the choir. This process of geometric propagation meant that every part of the structure, from the largest wall to the smallest window, was mathematically related. It was a system of self-similarity where the logic of the whole was reflected in every part. This is why a cathedral feels so unified and harmonious, even when its decoration is wildly intricate. The underlying order is always there, an invisible armature of divine ratios holding up the visible splendor. So how did this abstract play of lines and circles on a tracing floor translate into a mountain of perfectly cut stone? This grand geometric vision needed a physical anchor, a place where the master's mind could meet the mason's hands. That anchor was the tracing floor, a vast, flat canvas of plaster or stone, often located in a dedicated lodge near the construction site. Etched into its surface with charcoal and chalk was a sprawling web of lines, a full-scale map of the cathedral's most complex components. This was the master mason's live design studio, where he translated the sacred geometry of circles and triangles into the tangible profiles of arches, windows, and vaults. Every sweeping curve of a window tracery, every precise angle of a rib that would soar 100 feet overhead, was first drawn here at a 1-to-1 scale. The true genius of this system lay in its next step. From these intricate floor drawings, craftsmen would create precise wooden templates. A carpenter would carefully trace the lines of a specific arch or column capital onto thin pieces of wood, then cut them out. These templates were the ultimate instruction manuals handed to the stonecutters in the yard. A stonecutter, who might never see the final building take shape, would place his wooden template onto a rough block of stone and trace its outline. His job was then to carve that single, perfect piece of a vast, three-dimensional puzzle. This process transformed abstract design into flawless physical reality. It was a system of medieval mass production and rigorous quality control, ensuring that a stone carved in a workshop miles away would fit perfectly against its neighbor on the dizzying heights of the scaffolding. The tracing floor was the silent, indispensable link between the master's divine blueprint and the mountain of raw stone, a process that empowered hundreds of individual artisans to build as one. But how did these perfectly carved stones, some weighing many tons, defy gravity to reach their place in the sky? Before a single stone could touch the sky, it had to be coaxed from the earth. The true genesis of a Gothic cathedral was not in the architect's mind, but in the dark, cavernous quarries that pockmarked the landscape. Here, quarrymen, their world filled with the constant ring of metal on stone, performed the first act of transformation. Their primary tool was a deceptively simple one, the feathered wedge. They would drill a line of holes into the bedrock, then gently tap pairs of iron wedges, each with a thin metal feather on either side, into the stone. With rhythmic, careful blows from a sledgehammer, they would tighten each wedge in sequence, creating an immense, controlled tension along a precise line in the rock. Then, with a final, sharp crack that echoed through the quarry, the earth would give up a perfect block, sometimes weighing several tons, cleaved as cleanly as if cut by a giant's knife. This was not brute force, it was applied physics, a deep understanding of stone's inherent weaknesses. Once freed, these rough, monolithic blocks began their journey to the lodge yard, the cathedral's open-air workshop. This was the domain of the stonecutter or banker mason. Surrounded by a symphony of tapping and scraping, he was a true artist of geometry. His tool kit was a collection of specialized chisels, punches, and mallets, each designed for a specific task, from roughing out a basic shape to carving the finest decorative detail. His most crucial guide, however, was not a tool but a template, the wooden pattern taken directly from the master's tracing floor. Laying this template on the stone, he would trace its outline and then begin the meticulous process of cutting away everything that was not the perfect architectural element. With every strike of his mallet, the rough stone shed its earthly form, becoming a precise voussoir for an arch, a delicate fillet for a rib, or a sculpted leaf for a capital. But in a project involving tens of thousands of nearly identical stones, how could anyone possibly know where each one belonged? The answer lay in a simple, ingenious code. As he finished his work, the stonecutter would carve a small, unique symbol onto a hidden face of the block, a banker mark. One stone might bear a single vertical line, another 3 intersecting circles, another a symbol that looked like a tiny fish. These were not signatures but assembly instructions. This simple marking system meant that a laborer high on the scaffolding, who had never seen the master plan, could look at a stone marked with a specific set of lines and know with absolute certainty that it was the 5th corbel on the north wall. The stonecutter's skill breathed a kind of life into the rock, giving it a specific identity and destiny within the greater structure. He was crafting the very DNA of the cathedral, one perfectly shaped, uniquely coded block at a time. And with the mountain of stone ready, the next, even more daunting challenge began, moving this geological puzzle to the heavens. That mountain of perfectly carved stone now faced its greatest challenge, the pull of the earth itself. To lift a single 2-ton block to the top of a tower 150 feet in the air required a machine of immense power and cleverness, a machine powered not by engines but by human feet. The medieval treadmill crane was the great engine of the skyward ascent, a wooden giant that stood at the very heart of the construction site. Picture a massive wooden wheel as tall as 2 men, enclosed within a sturdy timber frame. Inside this wheel, men would walk, their steady, plodding steps causing the great axle to turn. This was not a hamster wheel of frantic activity, but a slow, deliberate, and coordinated effort, a human gear in a machine of immense leverage. Their footsteps on the slats of the wheel translated into the groaning turn of the central axle, which then wound a heavy rope, hoisting the stone inch by deliberate inch into the heavens. The true genius of this machine, however, lay not in its power but in its safety. A heavy stone dangling high above a busy work site was a catastrophe waiting to happen. The medieval engineers solved this with a brilliant mechanical bite, a device called the pawl. This was a simple wooden or metal bar that engaged with a ratchet wheel on the axle. With every step the men took forward, the pole would click, click, click against the teeth of the ratchet. But if the men stopped or slipped, the pole would immediately catch, locking the axle in place and preventing the heavy load from plummeting back to the ground. This simple mechanism gave the workers control, allowing them to rest or reposition the load with absolute confidence. The crane did not work in isolation. It was the pinnacle of a temporary wooden city, the intricate web of scaffolding that encased the growing cathedral. This lattice of timber provided not just platforms for the masons to stand on, but the essential anchor points for the cranes themselves. The entire site was a symphony of coordinated motion, with teams of men in multiple treadmills working in shifts, their synchronized labor making the impossible routine. It was this marriage of human strength and simple, brilliant mechanics that gave physical form to the Gothic dream, placing stone upon carved stone in a slow, deliberate dance towards the clouds. But this entire breathtaking process from quarry to crane relied on a hidden financial engine, a river of wealth that funded decades of labor and innovation. High above the ground, the real work of assembly began, but it could not happen in thin air. Before the masons could lock the final keystone into a vault, they needed a stage in the sky, a temporary wooden world built with the same ingenuity as the stone one it supported. This was the art of the timber scaffold, a vast and complex skeleton that encased the growing cathedral. It rose level by level with the stone walls, a labyrinth of platforms, ladders, and catwalks that transformed the open air into a multi-story workshop. The entire structure was a testament to the carpenter's skill, assembled without a single metal nail. Instead, joints were carefully notched and lashed together with strong ropes or secured with wooden pegs. This flexibility was not a weakness but a strength, allowing the entire framework to shift and breathe alongside the stone it embraced, absorbing the vibrations of constant work and the changing weather. This temporary forest had one overwhelming job: to be strong enough to hold teams of masons, their tools, piles of mortar, and the heavy stones being winched up by the cranes that were often mounted directly onto its strongest frames. Its design was a feat of practical engineering, calculated to bear immense and shifting loads, yet its most remarkable feature was its own destiny. Once the final stone was set and the mortar cured, this intricate wooden city was systematically dismantled. The timber was cleaned, sorted, and stored, ready to be reused on the next great project. The scaffold was a ghost, a vital but vanishing infrastructure that left no trace on the finished monument, its only legacy the impossible stonework it made possible. This entire wooden city in the sky had a single, most critical purpose: to hold the very soul of Gothic architecture in place before it could stand on its own. That soul was the stone arch. You cannot build a curved structure from individual blocks in midair. They would simply collapse under their own weight. The solution was a temporary wooden skeleton known as centering. For every single arch, every delicate window, and every soaring rib vault, the carpenters first had to build a perfect, full-scale model out of timber. This centering was the ghost shape of the future stone, a custom-made cradle for every curve. The carpentry required was extraordinarily complex. These were not simple semicircles, but pointed Gothic arches, parabolic curves, and intricate intersecting ribs. Each piece of the wooden frame had to be individually cut and joined to create these compound shapes with absolute precision. The strength demanded was immense. A single arch centering had to bear the colossal weight of dozens of stone blocks, all slathered in wet, heavy mortar, without sagging even a fraction of an inch. It was a test of the carpenter's skill as much as the mason's. The moment of ultimate truth came when the mortar had finally cured. This was called striking the centering. Work would halt and a tense silence would fall over that section of the scaffold. The carpenters would then carefully knock away the wooden supports. This was not a violent demolition but a delicate, controlled dismantling. As the last piece of wood was removed, the arch was left completely alone, a perfect stone chain holding itself in the air. In that breathtaking moment, the theoretical geometry of the tracing floor and the perfect cuts of the stonecutter were put to the ultimate test. If the calculations were correct and the craftsmanship true, the arch would stand, a permanent monument to a temporary wooden frame that had already vanished. The true magic of Gothic architecture is that its walls are not walls at all. They are vast, luminous canvases of colored glass, held in place by a stone skeleton that remains mostly unseen from within. This is the legacy of the flying buttress, the most revolutionary innovation in the entire Gothic arsenal. To understand its necessity, you must first feel the invisible forces at play inside the cathedral. High above your head, the magnificent stone vaults are not just a ceiling, they are an engine of immense outward thrust. The weight of all that stone channeled along the curved ribs does not simply press down. It pushes sideways, trying to splay the tall, slender walls outwards like a house of cards. For the Romanesque builders, the solution was brute force, thicker and thicker walls, which meant fewer and smaller windows. But the Gothic dream was a wall of light, a cage of stone so efficient it could be mostly replaced with glass. This dream was an engineering impossibility until they moved the support system outside. The flying buttress is essentially a stone arm, a graceful arch that leaps from a massive, free-standing pier on the outside of the building to connect with the main wall at the precise point where the vault's thrust is greatest. Think of it like setting a heavy ladder against a wall you are trying to push over. You lean your shoulder into the wall, but a friend braces the top of a ladder from the outside, their own weight counteracting your push. The flying buttress does exactly this. It catches the wall's desire to fall outward and redirects that dangerous lateral force, channeling it down the sloping curve of its own stone back, and finally down into the massive vertical pier anchored deep in the ground. This externalized the entire structural dilemma. The deadly push that would have shattered a conventional wall was now transformed into a simple, manageable load of downward pressure. This exoskeleton of stone arms, often stacked in 2 tiers for the highest naves, created a perfect equilibrium. The push of the vaults from the inside was met by the equal and opposite counter, thrust from the buttresses on the outside. The wall itself, now liberated from its load-bearing duty, could be pierced with the enormous, traceried windows that fill these spaces with unearthly radiance. The flying buttress was the final, crucial piece of the puzzle, the ingenious lock that made the stone cage stable and the wall of light possible. Look up. The ceiling of a Gothic cathedral is not a solid stone slab. It is a stone skeleton, a delicate web of arches that transforms the immense weight above into an elegant geometric dance. This is the rib vault, the brilliant innovation that turned the heavy, tunnel-like ceiling of the Romanesque era into the lofty, light-filled space of the Gothic dream. Before this, builders relied on the barrel vault, a massive, continuous arch of masonry that felt like being inside a stone tunnel. It was oppressive, dark, and its weight pressed down evenly along the entire length of the supporting wall, demanding those thick, windowless structures we saw earlier. The rib vault changed everything. Think of it not as a ceiling, but as a permanent scaffold made of stone. The master masons would first construct the ribs themselves, these slender, arched bones of stone that crossed the space between columns. These ribs created a predefined, stable framework right from the start. Once this stone skeleton was locked in place, the builders could fill the spaces between the ribs with a thin, lightweight stone paneling called the webbing. This was the real breakthrough. The heavy, structural work was done by the robust ribs, which channeled all the weight of the ceiling down onto specific, predetermined points, the tops of the slender columns below. The webbing simply filled the gap. It did not have to be thick or strong. This method was incredibly efficient. It was like building a modern umbrella. The strong metal ribs define the shape and carry the load, while the thin cloth simply covers the space. By concentrating the forces, the rib vault allowed the ceiling to be both taller and visually much lighter. It also gave the masons new freedom. They could now design complex bay systems, creating a rhythmic, modular interior space that pulls your eye down the entire length of the nave. This elegant stone web overhead is the final, crucial link in the structural chain. The ribs gather the weight and send it down the columns transfer it to the arches, and the flying buttresses outside catch the outward thrust. Every element works in perfect, silent harmony, a symphony of balanced forces that made the wall of light not just a spiritual aspiration, but an engineering reality. Without a single ruler or tape measure to guide them, the medieval builders achieved a consistency that seems almost supernatural. The secret was the template, a physical key that unlocked geometric perfection across decades of work and generations of craftsmen. Carved from thin sheets of wood or beaten metal, these patterns were direct descendants of the master's full-scale drawings on the tracing floor. A master mason would not hand a stonecutter a complex set of written instructions or a numbered diagram. He would hand him a piece of wood cut into the exact profile of a window mullion or the precise curve of an arch. This simple object held the entire design language of the cathedral in its silhouette. The stonecutter in his yard would place this wooden guide onto a rough block and trace its outline with a metal scriber. His entire job then became one of removal, carefully carving away everything that lay outside that line until the stone perfectly matched the template's form. This process turned abstract geometry into a tangible, repeatable action. A young apprentice could be taught to follow the wooden pattern with unwavering accuracy, ensuring his work would match that of a master who had passed on years before. This was medieval mass production, a system of interchangeable parts conceived centuries before the Industrial Revolution. It meant that the 10,000 stones for a vast vaulted ceiling, each one slightly different from the next, could be carved by hundreds of different hands in scattered workshops, yet when they arrived at the site, they would lock together as if carved from a single, immense block. The template was more than a tool, it was a vessel for knowledge. In a world where few could read and complex mathematics were the domain of scholars, this physical object carried the intelligence of the entire project. It embedded the master's wisdom directly into the workflow, ensuring that the sacred proportions of the tracing floor were faithfully reproduced in every single stone, from the foundation to the highest spire. This silent, object-based communication guaranteed that the cathedral's geometric soul remained pure from the ground up. Once a crane had lifted a stone to its final level, the real test of finesse began. A block weighing several tons now had to be shifted sideways, rotated, and settled into its exact position with the precision of a jeweler setting a gem. The solution was not more power but more intelligence. For this delicate final dance, the builders turned to the simplest and most profound machine of all, the lever. A strong wooden beam, perhaps 20 feet long, placed over a sturdy fulcrum of oak, could transform the effort of a few men into an irresistible force. One team would press down on the long end of the lever, creating a gentle, controlled lift at the other end. another team, working in perfect coordination, would use crowbars to nudge the stone forward an inch at a time. With patience and rhythmic effort, they could walk a multi-ton block across the platform and into its perfect, predetermined home. This was physics made visible, an intuitive mastery of mechanical advantage that turned immense weight into manageable effort. But how did they coax stones up the temporary wooden ramps that crisscrossed the scaffolding? For this, they relied on another elemental principle, the inclined plane. A long, sloping ramp of heavy timber, its surface slick with animal fat or soap, became a path of least resistance. Teams of laborers using ropes and rollers could slide a massive stone upwards with a steady, distributed pull. By extending the distance over which the force was applied, the ramp dramatically reduced the effort needed at any single moment. This was not about brute strength, but about outsmarting gravity itself. These builders did not calculate force vectors or coefficients of friction. Their knowledge was written in the calluses on their hands and the worn grooves of their tools, a deep, generational wisdom passed from one craftsman to the next. They understood that with a long enough lever and a low enough slope, human strength could achieve the work of giants. This elegant efficiency echoed throughout their entire hoisting systems, proving that the true secret to their success was not magic, but a profound and practical partnership with the fundamental laws of the physical world. Yet for all its immense power, the great treadmill crane had a delicate problem. Its strength was perfect for hoisting standard blocks, but a cathedral is not made of blocks alone. It is crowned with intricately carved pinnacles, adorned with sculpted saints, and fitted with uniquely shaped keystones, all far too fragile to be slung in a rope net. Lifting these precious objects required a different kind of machine, one that traded raw power for absolute finesse. The answer was the windlass, a deceptively simple horizontal winch that became the surgeon's hand of the medieval building site. Imagine a large wooden drum mounted on a sturdy frame with a long crank handle on each end. Teams of men would turn these handles, winding a strong rope onto the drum. This setup provided a much finer degree of control than the massive treadmill. The men could turn the crank inch by inch, feeling the tension in the rope, and stop on a dime to make minute adjustments. It was the perfect tool for the final, precise positioning of a multi-ton stone angel or the central keystone of a vault. But a controlled lift is useless if the object itself cannot be gripped securely. You cannot simply loop a rope around a finely carved piece of stonework without risking a catastrophic chip or crack. This challenge was solved by one of the most elegantly simple tools in history, the Lewis iron. This was not a clamp or an external cage. It was a device designed to work with the stone, not against it. Before a critical stone was even lifted, the stonecutters would carve a special, dovetail-shaped hole into its top surface. The Lewis iron itself was a set of 3 pieces, a central tapered tongue flanked by 2 outward slanting wedges. These pieces were inserted into the prepared hole, and then the central tongue was tapped downward with a hammer. This action forced the 2 outer wedges to splay outward, biting firmly into the stone walls of the cavity. A shackle was then attached to the top of the central tongue. When the windlass began to lift, the force pulled the central tongue upward, which in turn drove the wedges even more tightly into their sockets. The harder the lift, the stronger the grip became. It was a self-activating, fail-safe mechanism that held the stone in a perfect, invisible embrace. No external straps, no risky pressure points, just pure, intelligent physics. The combination of the windlass and the Lewis iron allowed the medieval builders to perform what seemed like magic, gently lowering a massive, delicate sculpture onto its pedestal high on the facade, as if placing a jewel in a crown. This gripping and hoisting duo handled the most important pieces of the cathedral's fabric. ensuring that the artistry of the ground could safely and perfectly find its place in the sky. Yet every perfectly carved stone was utterly powerless without a hidden partner. The true strength of the cathedral lay not just in its stone skeleton, but in the chemical magic that bound it all together. This was the art of medieval mortar, a humble paste of lime, sand, and water that served as the structure's lifeblood. Its creation began with a transformation as dramatic as any on the building site. Quarried limestone was baked in a roaring kiln for days, driving off its essence until it became a crumbly, volatile substance called quicklime. The true alchemy happened next in a process known as slaking. When water was carefully added to the quicklime, it did not simply mix, it erupted. The material would hiss and steam, reaching temperatures hot enough to boil water, a vigorous reaction that required great care from the workers. This was not a simple mixing of ingredients, it was a controlled rebirth, turning a brittle rock into a potent, plastic binder ready for its purpose. The final mortar was a careful recipe of this slaked lime, mixed with clean sand and just enough water to create a workable paste. Its quality was everything. The mortar had to possess a unique duality, hard enough to lock multi-ton blocks in place for 1,000 years, yet flexible enough to allow the entire structure to breathe and settle over time without shattering. A mix that was too rigid would crack under the slightest shift, while one that was too weak would crumble into dust. The mason placing each stone was not just a builder, he was a chemist. He would carefully trowel a fresh bed of this mortar, then set the stone with a gentle twist, ensuring the glue spread evenly and expelled any trapped air. This created a perfect, uniform bond, a thin, resilient layer that distributed weight and stress across the entire surface of the stone. That simple bed of mortar was the silent, forgiving joint that allowed the rigid stone to move as one living entity, a technological triumph in a wooden bucket that has held firm for centuries. A single inch of error at the foundation could multiply into catastrophic failure 100 feet in the air. In this world of complex geometry and immense weight, the ultimate authority was not a master mason's eye, but the silent, unwavering pull of the earth itself. The tools that enforced this law were breathtaking in their simplicity. The first was the Plumb Bob, little more than a pointed lead weight suspended from a string. Yet when held against a rising wall, this humble device became the absolute judge of vertical truth. The string, pulled taut by gravity, pointed directly to the center of the earth, creating a perfect reference line that no human measurement could ever match. Any stone that dared to bulge outward or tilt inward was immediately revealed by the gap between the wall and the string. It was an unforgiving standard, but one that guaranteed the towering walls would rise straight and true, generation after generation. Vertical perfection, however, was only half the battle. Every single course of stone also had to be perfectly level. A sloping layer would introduce a subtle but relentless lean, dooming the entire structure over time. For this, the builders relied on another ingenious marriage of wood and gravity, the frame level. This was a wooden frame shaped like a capital A, with a carefully scribed mark at the very center of its crossbar. From the apex of the a Plumb Bob line was hung. The principle was infallible. When the two legs of the level rested on a surface, the mason would simply watch the hanging string. If it aligned perfectly with the mark on the crossbar, the course was level. If the string drifted to the left or right, the stone beneath one leg was too high or too low. It was an instant visual diagnosis, a tool that translated an abstract concept into a clear, binary readout. In the chaotic, dusty tumult of the worksite, amidst the shouts of laborers and the groan of cranes, these two rudimentary tools provided a sanctuary of certainty. They proved that the most sophisticated engineering does not always require complex machinery. but a profound understanding of a simple, reliable principle. The Plumb Bob and Level were the quiet guardians of the Gothic dream, ensuring that every stone, from the deepest foundation to the highest spire, answered to the same eternal gravitational call. The great stone puzzle was held together by a hidden iron heart, beating in the heat of the blacksmith's forge. While the masons shaped the cathedral's bones, the smith was its vital organ, crafting the ligaments and sinews that gave the stone giant its strength. His workshop was a world of fire and rhythm, a constant hiss of bellows and the ringing hammer blows that turned raw iron into the essential lifeblood of the entire operation. Every wooden joint in the vast, temporary city of scaffolding relied on the nails he forged, every complex centering frame, holding the shape of an arch until the mortar cured, was assembled with his iron spikes. The stonecutter's chisels, the carpenter's adzes, all the tools that wore down with daily use, were constantly repaired and re-sharpened at his anvil. Without this constant supply of fresh, sharp metal, the entire project would have ground to a halt in a matter of weeks. But his most crucial work was for the stone itself. The master builders understood that pure compression was not always enough. In places of immense stress, like the great rose windows or the slender pillars of the clerestory, they needed to bind the stone with metal tendons. The smith would forge heavy iron cramps, long bars with ends bent at right angles. These were set into specially carved channels in adjacent stones and sealed with molten lead, creating an invisible metal staple that locked the masonry together against any outward pull. He also produced long iron ties, rods that could stretch across a wide space to counter the thrust of a vault, tying the entire structure together from within. This was a profound symbiosis of materials, stone excelling in compression and iron in tension, working in a silent partnership. The smith's mastery allowed the builders to push their designs to the very limits of stability, reinforcing critical points with just enough metal to make the impossible stonework hold fast. His forge was a crucible of necessity, transforming raw ore into the delicate yet unbreakable threads that stitched a dream of stone into a permanent reality. But all this stone and mortar was useless without a river of another kind flowing constantly through the site. The foundation trenches, dug deep into the earth, were perpetually threatened by groundwater, a silent enemy that could turn a building pit into a muddy lake overnight. Before a single stone could be laid for the glory of God, the builders had to win a daily battle against the water under their feet. Their first line of defense was a network of drainage ditches, carefully engineered to channel this seepage away from the excavation. These trenches fed into deeper, brick-lined pits known as sumps. Here, in a relentless cycle of labor, workers would use simple buckets to bail out the accumulating water, hour after hour, day after day, keeping the precious foundation dry and stable. It was back-breaking, monotonous work, but it was the uncelebrated chore that made the celestial architecture possible. Yet they needed water as much as they fought it. A project of this scale was a living city of its own, with hundreds of workers and their animals requiring a constant, clean supply for drinking and washing. More critically, the alchemy of mortar demanded vast quantities of water to slake the quicklime and mix the final paste. How did they solve this dual challenge of removal and supply? They became masters of redirection, using a technology perfected by monastic communities for their own water management. The builders would construct canals and leats, small artificial channels that diverted water from a nearby river. They used nothing more than wooden shovels and sheer manpower to sculpt the landscape, creating a gentle, controlled gradient that brought a steady stream of fresh water directly to the lodge yard. For lifting this water to where it was needed, they employed clever pumps, often powered by a treadmill or a walking wheel. not unlike the ones used for the cranes. These simple hydraulic systems were the site's invisible circulatory system, a triumph of medieval earthworks that ensured the foundation was never too wet to build upon, and the mortar mix was never without the water that gave it life. This practical, ground-level ingenuity was the silent, muddy prerequisite for every soaring vault and radiant window, the humbling truth that the path to the heavens began with a ditch. While the master mason held the geometric soul of the cathedral in his mind, another, more earthly kind of genius was at work on the ground. The construction site was a voracious, unrelenting machine that consumed stone, timber, and food at a staggering pace. Keeping this machine fed was a logistical miracle in its own right, a triumph of medieval organization that rivaled the engineering of the arches themselves. Think of the supply chain as the cathedral's circulatory system, a network of veins and arteries pulsing across the countryside. From specialized quarries miles away came the finest limestone, loaded onto wooden carts pulled by teams of oxen. These carts, their wheels groaning under the weight, moved at a walking pace, perhaps only 10 miles on a good day. For truly massive stones or long distances, the builders turned to the natural highways of the era, the rivers. Heavy, flat-bottomed barges, poled by teams of bargemen, could carry dozens of blocks at once, gliding silently past villages and fields until they reached the wharves built just for the cathedral project. This was not a one-time delivery. It was a continuous, decades-long flow, a river of stone flowing steadily toward the rising walls, but stone was only one ingredient. The temporary city of scaffolding and centering devoured entire forests. Timber had to be felled, squared, and transported, often from lands owned by the church or granted by a local noble. The scale of consumption was breathtaking, requiring a sophisticated understanding of sourcing, transport, and storage that would challenge a modern project manager. And at the heart of this logistical web were the people. Hundreds of skilled workers and laborers could not build on an empty stomach. A separate, parallel supply chain was dedicated entirely to sustenance. Vast quantities of grain, ale, and preserved meat had to be sourced, purchased, and delivered daily. Bakers, brewers, and butchers worked in shifts to feed the army of builders, their work as essential to the cathedral's rise as the mason's trowel. This entire sprawling operation, from quarry to kitchen, required a constant river of another kind, money. Wealthy patrons, from bishops to merchant guilds, provided the funds, but it was the clerks and stewards who managed the accounts, paying the carters for their loads, the bargemen for their trips, and the workers for their labor. This intricate dance of supply and demand, of procurement and payment, was the invisible engine of the entire endeavor. Without this non-technological technology of management and economics, the visionary design would have remained a beautiful drawing on a dusty tracing floor, a dream of stone that never found its way to the sky. The final piece of the Gothic miracle was not stone at all, but light itself. Those towering walls, made possible by the flying buttress, were now ready to receive their true purpose, immense windows that would transform plain sunlight into a divine language. This was the art of stained glass, a form of frozen light created through a blend of ancient alchemy and meticulous craftsmanship. The magic began not in a glazier's workshop, but in a furnace that resembled an alchemist's laboratory. The primary ingredient was ordinary sand, but to make it into glass, it had to be fused with a flux, a substance that would dramatically lower its melting point. This flux was potash derived from the burned ashes of certain trees. When this sand and potash mixture was heated in a clay crucible within a roaring furnace, it melted into a viscous, greenish liquid. This base glass was the canvas, but the glorious colors were the result of carefully guarded chemical recipes. master glaziers discovered that by adding metallic oxides to the molten mix, they could produce a stunning spectrum. A sprinkle of cobalt oxide created a deep, celestial blue. Copper compounds could yield rich greens or fiery reds, depending on the furnace's atmosphere. The most precious color of all was a ruby red, achieved by suspending tiny particles of gold within the glass matrix. This was a literal transmutation of base materials into something priceless and radiant, a true fusion of metallurgy and mystical art. Once cooled, this colored glass was not in the form of large, flat sheets. It was broken into smaller, manageable pieces, each one a unique fragment of pure, glowing color. The next challenge was to assemble these fragile jewels into a coherent, giant picture that could withstand the wind and the centuries. The tool for this was the lead came, an H-shaped strip of cast lead. A glazier would take the design, called a cartoon, which was a full-scale line drawing of the window. He would then select a piece of blue glass for a robe or red for a background and place it on the cartoon. Using a hot iron, he would score the glass along the outline of the design, then gently tap it to break it along the scored line, a process called grossing. Each piece, now cut to a precise, irregular shape, would be fitted into the channel of the lead cames. The glazier worked like a jeweler, building the window piece by piece, connecting the leads at every joint. Once the entire panel was assembled in this lead net, the joints were sealed with a soldering iron, creating a flexible yet incredibly strong metal web that held the glass fragments in a permanent embrace. This completed panel, weighing hundreds of pounds, was then the final piece of the puzzle. It was lifted into the stone opening of the traceried window and secured with durable iron bars called armatures, which were built right into the stonework. The result was a wall that was not a barrier to light but a translator of it. As sunlight passed through this mosaic of colored glass, it was transformed. The interior of the cathedral became a space bathed in a luminous, otherworldly glow, where biblical stories were told not with words but with light and color. This was the ultimate fulfillment of the Gothic dream, a space where heaven and earth met, not through stone alone, but through the alchemical magic of frozen, storytelling light. The soaring stone vaults did more than just lift the eyes toward heaven. They lifted the human voice into something transcendent. Within these cavernous spaces, sound itself was transformed, becoming a physical presence that washed over the congregation. The hard, polished stone of every column, wall, and floor refused to absorb the vibrations of a single voice or a choir's chant. Instead, it reflected the sound, bouncing it back and forth across the vast interior for many seconds after the initial note was sung. This long, lingering reverberation was not a design flaw. It was an acoustic alchemy that turned simple melodies into a thick, ethereal tapestry of sound. The complex geometry of the rib vaults overhead played its own part, scattering the sound waves in countless directions, creating a diffuse and enveloping halo of resonance that seemed to come from everywhere at once. A single monk's voice in the choir could be felt as much as heard, filling the entire nave with a presence that felt both immense and intimate. This was the cathedral's hidden auditory engine, an acoustic environment perfectly tailored to the slow, sustained notes of Gregorian chant and the emerging complexities of early polyphony, where multiple melodic lines would weave together without ever clashing into noise. The very shape of the building guided the sound with intention. The curved wall of the apse, the semicircular space behind the altar, acted as a massive natural sound reflector. It captured the voices of the clergy and the choir, focusing their chants and prayers and projecting them outwards, directly toward the congregation gathered in the nave. This subtle acoustic amplification ensured that the sacred words traveled clearly to the far reaches of the church, uniting everyone in a shared auditory experience. The materials chosen by the builders, each selected for structural integrity, became unwitting partners in this symphony. The dense limestone, the polished marble floors, the vast expanses of glass, all contributed to a bright, lively acoustic with a long decay. There was no soft fabric or plush seating to muffle the sound, only this brilliant, resonant chamber where every note could ring true. While we cannot know if the master masons fully understood the physics of sound propagation, they undoubtedly recognized the powerful emotional effect of this auditory environment. The combination of shimmering light from the stained glass and this enveloping, resonant sound created a truly multi-sensory form of worship. It was an experience designed to bypass the intellect and resonate directly within the soul, making the divine feel not just visible, but audible and palpably present in the very air one breathed. This knowledge was far too valuable to leave out in the open. The beating heart of this guarded wisdom was the lodge, a building within the building that served as workshop, drawing office, and sanctuary for the masons. Within its walls, the master's geometric secrets were protected with the same intensity a king would protect his treasury. This was not a place of dark magic, but of profound practical intelligence. Here, the complex designs from the tracing floor were translated into the wooden templates that guided every stone. Here, senior masons trained the next generation not with textbooks, but through hands-on demonstration and carefully guarded oral tradition. An apprentice would spend years learning the sacred proportions, the correct way to hold a chisel, and the subtle feel of stone that was perfectly cut, all under the watchful eye of his master. This was a complete education system, but one hidden from the outside world. To protect this intellectual capital, the masons developed a silent language of symbols. A simple mark carved into a stone was not just a signature, it was a resume. A complex geometric sign might identify a specific master mason or denote membership in a particular lodge. When a traveling mason arrived at a new site, he could present his personal mark, a kind of medieval professional credential that proved his training and granted him entry to work. This system of symbols extended to the stones themselves, with banker marks ensuring that each piece found its correct place in the grand design. This culture of secrecy was the era's most robust form of intellectual property law. A guild's unique method for designing a more elegant flying buttress or a stronger vault was its competitive edge. This knowledge guaranteed future commissions, prestige, and a steady flow of wealth to its members. Losing a design to a rival guild could mean financial ruin, so they built a human fortress around their techniques, a social technology of trust and initiation that safeguarded the data which allowed stone to fly. This carefully controlled transfer of skill ensured that the revolutionary principles of Gothic engineering could spread across Europe, yet remain exclusively in the hands of the few who had earned the right to wield them. The ambition to touch the heavens sometimes led to a terrible lesson in gravity. For all their geometric wisdom and engineering genius, the medieval master builders were navigating the absolute limits of the possible, and sometimes the stone itself would deliver the final, crushing verdict. The collapse of a tower or the sudden cracking of a vault was not just a construction delay, it was a profound and costly failure that shook the entire community. These events were the brutal but essential research and development of the Gothic age. Each disaster forced a deep and painful re-evaluation, pushing the technology of building to new levels of resilience. Perhaps the most famous example of reaching too far, too fast, is the choir of Beauvais Cathedral in France. The builders there sought to create the highest vaulted ceiling in all of Christendom, an unparalleled testament to their faith and skill. They pushed the slender stone pillars and the flying buttresses to an extreme never before attempted, and for a short, glorious time it stood. Then, in 1284, the choir vaults, soaring to a breathtaking 157 feet, gave way. A large section of the structure came down in a thunderous roar of shattered stone and dust. The precise cause is still studied by engineers today, but it is believed the vertical piers were simply too slender and the buttressing insufficient to handle the complex forces and wind loads at such a daring height. The collapse at Beauvais was a watershed moment. It was a catastrophic and expensive failure, but it was not the end. Instead, it became a masterclass in structural limits. The subsequent repairs incorporated thicker piers and a revolutionary double tier of flying buttresses, a direct and practical response to the forces that had brought the first attempt down. This painful learning process was repeated across Europe. A tower might lean ominously because its foundations were laid on unstable ground, teaching later builders to dig deeper and wider. A wall might bulge outward because the counter-thrust of the buttresses was miscalculated, leading to more robust designs. There were no textbooks for this. The knowledge was written in rubble. Each failure added a new, hard-won chapter to the collective understanding of how stone behaves under stress, how wind interacts with immense surfaces, and how a foundation settles over decades. This empirical method, learning by doing and sometimes by falling, was the final, unspoken discipline in the builder's art. It was a slow, often heartbreaking accumulation of practical wisdom that ensured the next cathedral would be not just more beautiful, but stronger and more enduring than the last. The alignment of these stone giants was not confined to the earthly plane. A deeper layer of sacred geometry was written in the movement of the sun and stars, connecting the cathedral directly to the cosmos itself. On specific mornings of the year, a beam of sunlight would pierce the dim interior, not by chance but by precise design, striking a particular carving on a capital or illuminating a sacred altar on its feast day. This was not magic, but a profound application of astronomy, achieved with tools of elegant simplicity. The primary instrument for this celestial plotting was the gnomon, essentially a vertical rod that acted as a giant sundial. By carefully observing the moving shadow it cast over the course of a year, the master builders could map the sun's exact path across the sky at every season. They would mark the solstices, the points where the shadow was longest and shortest, and the equinoxes, when day and night were of equal length. This annual solar map was often permanently etched into the cathedral floor as a meridian line, a north-south marker that captured the sun's zenith at noon. With this understanding, they could then design the building's orientation and its windows with breathtaking intention. A specific window high in the eastern apse might be positioned so that only on the feast day of a particular saint, as the sun rose to a certain height in the autumn sky, a single, brilliant shaft of light would travel down the nave to land directly on the saint's reliquary. This transformed the architecture into a cosmic clock and a theological statement. It embodied a worldview where the earthly church was a perfect reflection of the divinely ordered universe, a microcosm built in stone. The alignment was a silent, yearly performed ritual, a technology that wove the fabric of the building into the very tapestry of the heavens, proving that their vision reached beyond the clouds to touch the mechanics of creation itself. That invisible skeleton of stone, perfected in the Gothic age, refused to remain confined to the cathedral. Its principles began a quiet migration, leaving the realm of faith to reshape the very fabric of our modern world. The flying buttress, for instance, did not vanish, it simply shed its decorative skin. You can see its fundamental logic in the massive, sloping abutments of a modern dam. Here, the immense thrust of millions of gallons of water is pushing against the concrete wall, just as the vaults pushed against the cathedral walls. And just like the medieval builders, modern engineers place a heavy, angled brace on the outside, channeling that horizontal force safely down into the solid bedrock. The same principle supports the long decks of major bridges, where the weight and traffic load are countered by external supports that function with the same essential geometry as those stone arms in the sky. This was more than a coincidence of form. It was a direct inheritance of a solved problem. The Gothic mastery of the skeletal structure was an even more profound leap forward. By creating a stone framework of ribs and columns, the masons proved that a building's skin did not have to bear its weight. This idea of a load-bearing skeleton is the very soul of the modern skyscraper. When you look at a steel-framed tower, you are essentially looking at a Gothic cathedral stripped of its stone infill. The steel I-beams are the ribs and columns. The curtain walls of glass are the updated version of the stained glass windows, and the entire system relies on the same fundamental separation between the structural frame and the weatherproof enclosure. This revolutionary concept that the support could be internalized and made incredibly efficient was first proven on an epic scale by those medieval builders. Their greatest contribution, however, was not a single invention but a way of thinking. They were the first true structural artists working from an empirical understanding of forces. They learned by observing, by building, and sometimes by tragic failure, how stone behaves under compression, how to redirect thrust, and how to create vast, open spaces. This hands-on wisdom, this deep, intuitive feel for the dance of weight and counterweight, laid the intellectual groundwork for the formal science of engineering that would emerge centuries later. The soaring atrium of a contemporary airport or shopping mall, with its light flooding through a vast glass roof, is a direct descendant of the cathedral nave. It is the same human desire for sublime, uplifting space, now answered with steel and polymer instead of stone and mortar, but made possible by a set of timeless solutions first carved into the skyline of medieval Europe.